Hello, today we are going to cover 11.1 permutation as well as 11.1 combination notes. So you guys will be able to count permutations and combinations by the end of this video. So the first thing we need to talk about is the fact that in a permutation order matters. You'll see what I mean in just a minute, but first we are going to look at the equation for a permutation. So it's NPR, that just means permutation, where N is the total number of things and R is the total number chosen. And the order matters for the order that they are chosen. So the equation for our permutation is N factorial, notice it's an exclamation point, over parentheses N minus R factorial. So a quick rundown of how factorials work. They are exclamation points. So for example, you would have 6 factorial. A factorial just means you multiply the number that is written by every number smaller than that. So 6 factorial is actually 6 times 5 times 4 times 3 times 2 times 1. 100 factorial is actually equal to 100 times 99 times 98 times 97 times 96. And keep on going. You multiply all the way down to times 1. Okay? So, we know that order matters in a permutation. So this example 1, we're going to know that we are going to use this permutation. When we get to combination slide, though, we're going to have to decide if it is a combination or a permutation. Anyway, there are 14 people eligible to be officers in the student council. How many ways can the president, vice president, treasurer, or secretary be chosen? So we know we have 14 total people. This is our N. It's how many total there are. And then there can be 4 people chosen for officers. And the order matters because if you choose the first person as the president, then that first person, if they were actually chosen third, would be treasurer, not president. So you have to keep the order in mind, okay? So we're going to use our equation, 14P4. So 14 things taken 4 at a time. So we have 14 factorial over 14 minus 4 all to the factorial. Notice it's not each thing factorial. So we have 14 factorial over 10 factorial because we need to simplify within our parentheses to start. And then a cool thing with factorials is the fact that if you take 14 times 13 times 12 times 11 times 10 factorial, 10 factorial stands for that times 9 times 8 times 7 times 6 and so on. So you can actually simplify factorials because these are both like writing out everything following and just cross them out because you know, we'll just write out a few of them. This keeps going. This keeps going. You know that they would just cancel each other out. So just imagine it continuing to cancel down the line here. So 10 factorial over 10 factorial can cancel out. And you are left with only 14 times 13 times 12 times 11. And if you plug that into the calculator really quick, you end up getting 24,024 possible choices for choosing the president, vice president, treasurer, and secretary out of those 14 people, which seems like a crazy lot. Okay? So I'm going to go ahead and go through this. If we were in class, you would try this on your own. There are 18 people running in a cross-country race. How many possible ways are there to place first, second, and third? Now, obviously, the order matters here. First is first, second is second, and third is third. So we have 18 total runners. And we have 3 places in the race. So the order matters means we're going to use our permutation, so 18 things taken 3 at a time. So we have 18 factorial over 18 minus 3 all to the factorial. That means we have 18 factorial over 15 factorial, which means we have 18 times 17 times 16 times 15 factorial all over 15 factorial. Those factorials cancel out. You have 18 times 17 times 16, which is equal to 4,896. Different ways that people could place first, second, and third. The next two examples, we are going to look at different words and how these letters can be arranged in different ways. So before we get to that, I want to talk about the word cat. We want to arrange these letters in all different ways. So the first one is just the original way. Then we can switch the last two letters. Still a new way to write it. Then we can take the last letter first and write the other two. And then we can switch the last two. And then we can take the middle letter and then we can switch the last two. So these are actually all of our ways. We have 6 ways. Or you can think of this as 3 factorial. 3 times 2 times 1 is equal to 6. So we can do the same thing with longer letters that we don't want to have to write out all the possible ways that these can be arranged. So the way we do this is we do total letters factorial, like we did with cat, over the repeats, because the repeats changed up a little bit. So our repeated letters are M twice, A twice, and T twice. So we have 11 total letters, so 11 factorial. Over each time there's a repeat, we do the number of repeats, in this case all 2's, times 2 factorial, because there are 3 letters repeated twice. This ends up giving us, when you do 11 factorial divided by 2 factorial times 2 factorial times 2 factorial, you end up getting 4,989,600 different ways to write the word mathematics. Let me tell you, I don't want to write all of those out. So I'm really glad we have permutation and factorials and all of these things to help us figure that out without having to do all of that writing, because I don't think I would even get 4 million, almost 5 million different things. I would be bound to miss at least a few. So now if we try the word apple, we can count how many letters there are. There are a total of 5 letters, so we have 5 factorial. And how many different ways can they be arranged? Now there is another duplicate here, so P is repeated twice, so we need to put a 2 factorial in the denominator. So I'll actually write this one completely out. We have 5 times 4 times 3 times 2 times 1, and 2 factorial is just 2 times 1. So these guys cancel out. This one's much simpler. You could maybe write all the different ways to write the letters of apple, 60 ways, but that would still take quite a time. Okay? So let's go ahead and move into combinations. Combinations, the order doesn't matter. So if you're forming groups of people and you don't care if they're getting a job, they just need to be in the group, or picking out items to take with you, that order doesn't matter either. That is going to be a combination. So there are mixed in throughout this page. So some of them will be combinations, some will be permutations, just as a heads up. So we have, once again, N and R, N things chosen R at a time. And this equation is similar in that it's N factorial But this time, it's r factorial, parenthesis, n minus r factorial. So, how many different groups of 3 could be made from the total number of students in this class? We're just going to say that there are 19 in class. You need 19 things chosen 3 at a time. The groups don't matter. It's not like you're choosing like writer and talker and all of those different things. You're just choosing 3. So we can plug this into our equation. 19 things chosen 3 at a time, so 19 factorial over 3 factorial, 19 minus 3 factorial. I like to go ahead and write it out just like this. Oops, I missed a number. 19, 18, 17, 16 factorial over 3 factorial, which is 3 times 2, times 16 factorial. I'm going to go ahead and cancel the 16 factorials. And then I just finish out this problem by taking 19 times 18 times 17 and then divide that by 6, because 3 times 2 is 6. So when we complete this problem, we end up getting that it's 969 different ways that you can make these groups of 3. Now, how many ways can 5 cards be chosen in a standard deck of cards? Now, there is a little bit of background knowledge that you need. You need to know that there's 52 cards in a deck. And we are going to use a combination because it doesn't matter the order that they're pulled. So we have 52 chosen 5 at a time. We can go ahead and set up this combination, set up the combination just like this. Now, I do want to show you that there is help on a graphing calculator. So if you go ahead and either flip over to your Desmos scientific calculator or grab a graphing calculator, you can go to this function here. If you're going to use a graphing calculator, I can help you in class on how to get that, and I'll actually write it on the notes too. So we have this combination button here. And to use Desmos, you actually have to plug it in like a coordinate, sort of, 52, 5, and then it'll solve it for you. You end up getting 2,598,960. If you were using a graphing calculator, it would actually just have boxes for you to plug in N and R. So that's how you can do that on your scientific Desmos calculator. Instead of doing all this work, you also probably saw that there was a permutation choice, an NPR. You could always use that too. Okay? So while I'm thinking about it, up here at the top, if you are going to use a graphing calculator, you will use, you will press the alpha button or the green key, then the window button, which is up on the top, and then you will either choose the 7, which is the permutation button, or the 8, which is the combination button. Either way, you'll plug in your numbers from there. All right, this next one, student council has 15 members that are eligible to be officers. Officer positions consist of president, vice president, secretary, and treasurer. How many ways can the officers be chosen? Now notice up here, they give us kind of a list of things to think about. And officers is one of our permutations. So this is the one that we're going to go back to using our permutations. 15 members. And we have 4 chosen as officers. So we have 15 chosen 4 at a time with a permutation, because order does matter now. So we have 15 factorial over 15 minus 4 factorial. This is 15 factorial over 11 factorial. These permutations are a little easier to do by hand than combinations, but I'll go ahead and show you how this works on the Desmos scientific calculator. You end up and hit the permutation button, and then you take and you go 15, 4, 15 things chosen 4 at a time, and you get 32,760 different ways you can choose these officers. Alrighty. The next one, we're once again talking about a race. A race has 315 participants. We want to know how they can score first, second, and third place finishes. So there are 3 places. Once again, we have a race here, places in a race. So we have 315 runners, chosen 3 at a time, or chosen 3 in a specific order, maybe I should say. We have the permutation set up. We can go ahead and use our Desmos calculator with a permutation once again. So we get 30,958,830. Different ways people could place. And then you have 8 books you want to read. You are taking 2 with you on your trip. How many ways can these 2 books be chosen? Now notice, it doesn't say what order would you read these books in or anything like that. It just says how can they be chosen. So we're back to combinations. The order does not matter. We have 8 books. 2 are chosen. So you have 8 things chosen, 2 at a time. You can set up your combination formula again, or just flip back to your Desmos calculator. Oops, don't want to do that. 8 things chosen, 2 at a time, and you get 28 different 2-book combos. And then lastly, maybe the most difficult, is a committee consists of 4 people. There are 4 men and 3 women who can be part of the committee. How many different committees could be formed if the committee has 2 boys and 2 girls? So we actually are going to do 2 different combinations and put them into one. So we have the combination of 4 possible men chosen 2 at a time, times the combination of 3 possible women chosen 2 at a time. If you were to plug these into your Desmos graphing calculator, the combination of men chosen 2 at a time is 6, and the combination of women chosen 2 at a time is 3. You go ahead and just multiply these, and you get 18 different ways this committee could be consisted. Okay? That is all for today. Have a great